welcome to lecture 30. So we will discuss real-time communication over packet switch networks. So mainly large networks, in some cases internet sized networks. So what are the real-time requirements for the internet? Well, we'll have to give preferential treatment to real-time traffic. What kind of real-time traffic? Voice, video conferencing, and also, this video that you're watching, you don't want any jitter, right? So some sort of a contract between the nodes and the internet service provider has to be established. So the internet service provider has to provide quality of service guarantees. Furthermore, the sender also has to provide some guarantees with respect to its rate of transmission that is not going to exceed certain bounds which are placed on the traffic. If let's say someone is not abiding by those guarantees that have been made, the ISP should have a method to handle such misbehaving nodes. So the main ideas are traffic shaping and policing, right? So the same way that we saw in the previous lecture, that the main ideas are global priorities and bounded access. So in this case, the idea is to adopt different scheduling policies at switches for ensuring that there is fairness among the different traffic flows. So there is a need to control the input rate at all connections, right? And if you look at the QoS architecture of the internet, protocols such as int serve and diff serve, etc., are important. So they are the ones which are in use. So at the time of setting up a connection itself, both the ISP as well as the sender need to send their requirements to each other. Particularly, the sender needs to specify the traffic characteristics. The ISP has to agree that yes, I can support that. And the moment that this agreement has been made, will the sender actually start sending and the connection will be established. So the question is that how do you characterize the traffic? So of course the bandwidth or the delay or the jitter are simple metrics, but we will look at different metrics throughout this chapter, multiple metrics. So the moment that the traffic has been appropriately characterized, we can reduce the network resources that need to be reserved, because after all, how can the ISP make a guarantee? It has to reserve some network resources, right, to make a guarantee, and also not over reserve, otherwise those resources will idle. So that is why we need to characterize traffic accurately and then work on that. So let us discuss one of the more common models known as the X-min S-max model. So the model is like this, that you are putting a minimum bound on the inter-arrival times between two packets. So you will say that, look, whatever is the case, it will always be more than a certain value, X-min. In a sense, I'll never, keep bombing packets. I'll have a minimum delay between them such that the network can react and process. Also, I'll have a bound on the packet size, in the sense the largest packet will not exceed S max. Right? So, in a sense, the server is constraining itself to the packet transmission frequency and the size of the packet. So, this will provide a tight bound for CBR traffic, in the sense that this value will be bounded by X min and this value will be bounded by S max. We could also have the RT model, where a node will satisfy the RT model if it generates no more than R into T bits of traffic for any interval T. You take an interval T, it will not generate more than RT bits. Again, you are quenching its bandwidth. Finally, we can have the X min, X average, S max, and I model, where we have introduced two more new parameters. One is X average and the other is I. So a connection will satisfy this model if it satisfies the X min S max model, and during any interval of length I, right? So you consider an interval of length I, regardless of the interval, right? So this will ensure that you are considering a large enough interval. You're looking at the average inter-arrival time. So the previous one was the minimum, but this is talking about the average. The average will be in the ballpark of x average, right? So you're saying that, look, whatever, even if you have some degree of variability, you're trying to quantify that variability in the sense you take a window of I time units. The average time will be x average. So in this model, you are bounding the peak rate and the average rate. So the peak rate is of course S max by X min. The average rate is X max, S max by X average, in the sense if you're still sending the largest size packets, but at least if this is the inter packet time, so this would be the average traffic rate. So this is a more accurate bound for VBR traffic. But what we'll also use is the sigma rho model. So the idea here is that a connection that satisfies this model, it will be that in any interval t, the number of bits generated by the connection is upper bounded by or less than. So this is an mx plus c kind of thing. So basically you draw a line like that, where basically sigma is the intercept and this is rho times t, where rho is the slope. So the thing is, this is the sigma rho model where it is sigma plus rho t. So this, in a certain sense is saying that, look, in a certain time interval, you will have this much of data. So it can be used to model bursty time sources, because for a very low value of t also, sigma will maintain its value. So this can be used to maintain a very bursty source, right? So it will basically, this is the burst, and this is again the constant amount of traffic, which is time dependent. Sigma is the time independent part. You can have multiple rate bounding, right? For over multiple averaging intervals, you could have that. So you could have R1, T1, R2, T2. Where you go back to the RT model, it would say that in T1 maximum you can send is R1 into T1. Then for T2 maximum you can send is R2, T2. So you could have multiple rates. So of course over any time interval I, the number of bits that is generated is bounded by RITI if I is between TI minus 1 and TI. If it's more than TI but less than TI plus 1, right, it will be Ri plus 1, Ti plus 1, that way. So as the averaging interval gets longer, you can sort of have the rate of the source, right? It will be of course lower than the peak rate and it will be quite close to its long term average. So this just follows from the law of large numbers. So the QoS framework will of course have to take into account these traffic models, be it the sigma rho model or the RT model, or the multiple bound RT model version, or the S max X min kind of model. So anytime we route packets, we do admission control, in the sense we set up a connection, we do rate control, and we will see something called service discipline and QoS renegotiation, in the sense if a certain QoS cannot be satisfied, we will try to negotiate the QoS once again. So for all of these things, these traffic models are required. So the key idea is that at the core of the network, of course you do routing, you figure out how to send the packet. You see if you can admit a call or not, in the sense whether you can do admission control. And then we will talk about something called a service discipline, which does the rate control. And then if nothing works, we'll try to renegotiate the QoS. So these are basically like the four pillars or the four blocks of our solution. So let's come to admission control, right? We'll discuss routing later. So you want to test whether the required resources are available. If they're available, you will set up a call. Otherwise, you will terminate. In the sense, you will say that, look, I don't have the resources. I cannot set up a connection. Now, coming to rate control, the idea is that whenever you set up a connection, you of course provide some statistics or some specs of the traffic that you are going to generate. Like in the case of the RT model or sigma rho, etc., these values are provided. So it ensures that the source, the rate control module, ensures that the source does not violate these. And then the service discipline is the one that provides resources to connections. and which ensures that these reservations that are made to essentially sustain the flow they hold, and these reservations were made at the time of establishing the channel itself. And finally, a renegotiation request can come either from the user who wants to change his own QoS requirement or from the network if there is new kind of congestion. So the QoS framework, as we have seen, this is the big broad framework at the ingress, at the input part of the network, at the core part of the network, and again at the egress, at the exit part of the network, which is finally connected to the destination. So let's now discuss the only module here that is left, which is routing. Packet routing basically means we need to find a path from the sender to the destination. At the time of connection establishment, we need to set up a path or a route. Of course, we could have multiple receivers. So then from a unicast kind of connection, it will become a multicast connection. So any routing algorithm can be used for such traditional protocols, including shortest path routing. But for traditional routing protocols, you will choose multiple paths which may not actually provide our QoS guarantees because these algorithms are optimized with respect to other metrics. Hence, there is a new discipline here in the area of real time communication, which talks about QoS quality of service routing or constraint based routing, right? Routing on the basis of some constraints. The primary goals are to select routes that meet certain QoS requirements. They are to increase the network utilization. For that, of course, you'll have to take a look at the topology of the network. You'll have to take a look at the resources that are available in terms of queues, buffers, etc. at multiple routers, the links that are available, the bandwidth that is available. You'll have to take a look at the complexity of the QoS algorithms, what are the constraints, and what exactly we are looking at, because there could be a multitude of variables like the hop count, the delay, the latency, right? The bandwidth, then the jitter in the delay, the non-determinism in the delay, the jitter. So we look at the QoS constraints. So let Dij denote a chosen constraint for link ij. We could have additive constraints in the sense for any path the constraints can add. For example, the delay of the entire path is delay ij plus delay jk plus so on and so forth. That's an additive constraint. So delay would add, jitter would add, the cost would add, the hop count would add. Then you would have multiplicative constraints where it will get multiplied, like let's say the noise or the reliability. So the reliability is fundamentally multiplicative because if you assume that the probability of a link failure, for example, if these are independent events, then independent events, these probabilities would multiply. So again, a multiplicative constraint can be converted to an additive constraint by taking a log on both sides. So then it will essentially become additive. You could then have what are known as concave constraints, where basically for the path, it will become the minimum of all of them. This is known as a concave constraint from the concavity of curves. So one such example will actually be the bandwidth. So the bandwidth is the idea is any chain is only as strong as the weakest link. So this is an example of a concave constraint. So the problem of finding a path is subject to two or more additive and or multiplicative constraints in any possible combinations. As I said, any multiplicative constraint also can be converted to an additive constraint by taking a log on both sides. So anytime we have that, actually the routing problem is NP complete, right? So you can deduce it, you can reduce it from the Hamiltonian cycle and other problems. So it's actually NP complete. So you can't find an exact solution, but that doesn't mean that you don't have good approximate solutions. So this assumes that all the considered constraints are independent. This is usually true for circuit switch networks where a circuit is established a priori. A long connection is established a priori. The delay and jitter and all of these things that we are trying to add or multiply also have to be known a priori or in advance. The delay and jitter of every link have to be known. So in packet switch networks, delay, bandwidth, and jitter are not really independent parameters across nodes, right? Even though in circuit switch they are, but in packet switch, it is kind of correlated. So you can't really add in the traditional sense, but you can always add to come up with an approximate solution. Now coming to different kinds of routing based algorithms, you can always use the classic shortest path algorithms like Bellman, Ford, or Dijkstra's algorithm, which we all study in a basic algorithms class, which is to compute routes using the hop count, delay, or jitter. So in that, of course, the idea could be that what are the more important constraints here. So the bandwidth is clearly very important, and also is the hop count, the number of hops that need to be traversed. That is also clearly very important. Delay and jitter are considered to be derivatives or corollaries of the bandwidth and hop count, but they are never considered primary factors in a network. So basically, bandwidth is typically the essential constraint. Even the hop count determines the complexity of the routing and the resource utilization. So coming to multicast routing, if you are doing multimedia applications, so let's say it's a Teams call and I'm teaching a class of 30 people, all 30 are the receivers. So we are talking of a multicast kind of scenario, right, with this voice over IP and video and so on. So point to point connection is a bad idea. It is impractical, leads to resource wastage. So what you use is you use a multicast tree where you could have multiple sources and destinations. All the sources are clearly not active at the same time, but clearly all the receivers are active at the same time, in the sense the entire class is listening. So I can sort of create a tree of receivers, right? And then I can multicast it to them. So I'll of course have to, co-opt a set of routers and links through which the traffic for maybe for a single source or a set of sources, in the sense, there could be multiple instructors in same set of students, or multiple people in a class. Maybe one person is presenting, then another person is presenting, or in a meeting there is one presenter, then there's one more presenter, and so on. So you could have multiple sources and multiple destinations. So destinations are also called sinks. So the multicast routing algorithm will be a tree which is rooted at a source. It should cover all the receivers, right? Naturally. And every path from the sender to each receiver, whatever be the path, should satisfy the quality of service or QoS constraint. So tree construction algorithms, there are two types of tree construction algorithms. One is source based, construction from each source. Other is core based, where basically you form like a core tree, and then any receiver that comes after that is sort of connected to the nearest node. So that is a core based algorithm. So here there is a very important protocol which is known as the resource reservation protocol, or the RSVP protocol, which is something that should be discussed in the context of routing and channel setup. Originally designed in 1993, it does scale to multicast communication. And what it does not do, it does not construct the tree, but given a tree, it reserves resources. And it also makes admission control decisions, in the sense whether I should set up a call or not. Well, that would depend upon whether you have the resources or not. And these decisions can be made by the RSVP protocol. So RSVP, what it would do is, for each destination, it maintains a sync tree, something like that. So basically, as opposed to a source tree, it is a sync tree where this is the destination or the sync, and we have all the nodes. A sync tree is a spanning tree, right? As is the case in most networks. It is routed at the destination and connects all the sources. So what it does is that you send control messages from each destination. So from here you send messages down the tree. We will see what these control messages are in a minute. So each router on the way would maintain two kinds of information. What is one is the state of the path, and the other is known as the reservation state. So what are the messages that are used? There is a path message and a reservation message, two kinds, right? Path and reservation. So the path state of each router basically is the path that is used by the multicast group. In the sense, if this is a multicast group and there is a router here, and let's say message is flowing from the source to the destination, so the path state will contain some information about the path. So this information is also used to maintain the sync trees of the destination. In the sense, for every destination also you maintain a sync tree, and this information is held by routers on the way. The reservation state essentially keeps track of resources which are reserved for different destinations. In the sense, you could have like two intersecting sync trees. All the routers on the way are basically sending traffic to either this destination over here or this destination over here. So given the fact that routers have a finite amount of buffer space, they can partition the buffer space between the two flows. In the sense, one flow like goes this way, other one uses this buffer space and goes that way. So that is why every router, which is in principle part of different source destination flows, will keep track of the resources that have been reserved for different destinations. So this is maintained in a table. So RSVP, as we have seen, because it maintains a sync tree, it's a receiver oriented protocol. So each router will receive messages from each downstream link in the multicast tree, and it will only pass a reservation message to its upstream link, right? So let us now look at the messages, the path message and the reservation message. So the path message by definition, as we have seen, is a control message. It doesn't really have any data with it. It is only for channel setup and resource reservation. So this is actually sent by the source. Okay, so it is sent by the source and forwarded by the routers in a multicast tree, because what the source is doing is that it is setting up paths to different destinations, right? So that is why it is sent by the source, and the routers basically forward it down the tree, and every node on the way understands the fact that a path is being created from this source to a bunch of destinations, and it is a part of at least one path. So the path message actually does the path setup. So each source will send its first path message before commencing transmission. That is obvious. And then, of course, as and when the set of receivers either increase, decrease, path messages are sent periodically. So it contains the specification of the flow, right? How the messages will flow. And whenever it receives a path message from a source, the router will update its path state. Then you can have other kinds of messages. So you can have the reservation request message. So each destination node, so now we are coming to the sync tree idea. It will send a different kind of message known as a reservation request message along the sync tree. So what happens in this case, we have a destination like this. It has a sync tree. It will send these reservation request messages. So what do routers on the way do? So it basically determines if, let's say, your downstream links, which are all these links that lead to a potential source, can they provide enough buffer space or the required reservation to sustain traffic? So basically, in this case, of course, the term resource has been made generic. In the sense, it could be bandwidth, it could be a buffer space on the router. So if whatever be the resource does not exist, it will reject the reservation requests. So in this case, primarily, what we are reserving is space to buffer the packets and the bandwidth to transmit. So it's actually both. So the resource, if that doesn't exist, in the sense that, let's say, it is not able to commit some bandwidth at least for transmitting the packet, and we are not able to create such a path to a source, then of course the reservation request will get rejected. So destination will first send its reservation message. When it receives a path message from a source whose message stream it wishes to receive, it will then so what happens? So first, what happens is that a path message is of course sent, and then every destination needs to ensure. So this is again a destination driven protocol. Every destination needs to ensure that there are sufficient resources along the way for it to receive a message. So that's the reason whenever it understands that some node somewhere wants to send a message to it, it will basically then in its sync tree send messages to reserve resources, where the resource that is being actually reserved is bandwidth and space on the routers, right? So that is what is being reserved. So if it can make the reservation, it will ensure that it can get the flow. Then again, the reservation has to be maintained, which means the destination has to periodically send reservation messages to ensure that the resources are not reclaimed. So this is known as a soft state that is maintained by the routers. So a quick analysis: any retransmission of messages in RSVP is an overhead, but it is an overhead in all protocols. But given the fact that these are short control messages, they are not long data messages, the overhead is in principle much lower. We can of course merge the control messages of different hosts or piggyback control messages with data messages. That will reduce the overhead if and where there is a need. And also we can minimize these messages when some information changes. But again, the key idea is like this, that we have sources and destinations. So initially when the source kind of lets all the destinations know that it wants to send something, it will send a path message. Each destination will now ensure. So this is where we become very destination specific, that on its sync tree, it will ensure that this given source finds some route through its sync tree via which it can reach it, and there are sufficient resources along the way. Now, coming to rate control QoS guarantees, just by admission control and then maintaining a service discipline, in the sense when the service is being provided, you are apportioning certain resources, right, for maintaining the service. This itself or by itself is not enough. In the sense, the sender may either accidentally, inadvertently, or maliciously exceed the rates that have been specified, right? So the sender may not kind of abide to the regulations that have been mutually approved or agreed upon. So this is where there is a need to prevent such misuse by rate control, because the sender and destination reach into an agreement that this is the amount of traffic that the sender will send. On the basis of that, the destination has contacted nodes in its sync tree and created a path for the sender to send with adequate resources reserved, which basically means that the sender and destination have an agreement via the nodes that comprise the path. But now if the sender starts sending more data, the entire agreement will break down. So that is why we need to perform rate control at the sender. So there are two ideas: traffic shaping and policing. So we have to choose which one to use. Again, depends on the application, the type of network, and the QoS requirements. So we will look at one example here, which is a token bucket with leaky rate control, which is by far one of the most popular algorithms in this space. So let's first look at traffic shaping versus policing. So the objective is the same, that we do buffer packets that are above committed rates. So the point is that the moment you exceed a rate, you don't drop the packets, but you store them somewhere. But in policing, you have a slightly high-handed approach in the sense you drop the excess packets, right? You don't buffer them. If there's a burst of data, so we will look at the leaky bucket algorithm, which kind of smoothens the traffic and delays it and so on. But in policing, what you do is you propagate the bursts. So again, as I said, policing is more of a knee-jerk mechanism as opposed to traffic shaping. The advantage of traffic shaping is given the fact that you're buffering, you avoid retransmission. The advantage of policing is that even though you drop packets and there'll be subsequent retransmissions, but at least in the network you don't create congestion and you don't create long queues. The disadvantages would be the reverse, that you create long queues, you create potential congestion. And again, because of the reduced retransmission in traffic shaping, again a disadvantage of policing would be that retransmission reduces actual throughput. So what is this algorithm, token bucket with leaky rate control? So you create a bucket which holds a pre-specified number of tokens, say small b. New tokens are generated and added to the bucket at the rate of R tokens per second. So this is something similar to that sigma rho model, where of course you generate it at the rate of R tokens per second, but again the bucket has a maximum capacity of B. So whenever a new token is generated, if the bucket contains less than B tokens, it's added to the bucket. Otherwise, if the bucket is full, the token in itself is ignored. So a waiting packet is taken up for transmission only if there is at least one token in the bucket. So in the bucket, right, you need to have at least one token. So then what you do is that you consume the token and then you send it up for retransmission. Sorry, so you send it up for transmission, not retransmission, just transmission. So if a sufficient number of tokens are not present, then of course your rate of sending gets reduced. So this is an example of essentially shaping traffic or providing a degree of rate control, in the sense that, of course your traffic can be bursty, in the sense, look, if you have a bucket and if the bucket has B tokens, then you can use all B's, it will become bursty, but then again the bucket will be empty and after that you can only transmit at the rate of R tokens per unit time. So the idea is that this is an example where it accommodates for some degree of burstiness, but still it provides for very good rate control. We can further augment this to make a better traffic shaper, where packets will wait until a bucket has a certain number of tokens. So as I said, there are many variants of this leaky rate control algorithm with buckets. But again, the key point is that this is a way of tackling small bursts and also providing at large time scales a uniform message throughput. So of course, in this case, we have an option of either buffering packets or discarding them, which is nothing but shaping or policing. The token is removed after the transmission of a packet, you will remove the token. So the maximum possible burst size is again B. So as I said, there is a connection between this and the sigma rho model, because the maximum number of packets that can enter the network in any interval of time t is RT plus B. Why? Well, B initially and then time t, so it's R. The rate is R, so it's RT plus B. So limit is basically set on the long-term average rate, right? So that we are setting. And if you divide this by t as t tends to infinity, it will essentially become R. So as I said, this is the key idea, that we have a token bucket where we are entering R tokens per second. Packets come, they stay in a queue, right? And if there are sufficient tokens, we remove a token and transmit a packet. And if the moment we don't have sufficient tokens, we just wait in the queue. And the moment the queue fills up, well, we will then have to discard package. We'll have to drop packets. We'll not have we'll not have any other way of dealing with the situation. So this again is, so we have basically seen all the four basic components or key components of a packet switch network. So we have looked at the sender, the receiver. We have looked at the switches on the way that transmit our packets. So there are of course parts of the switch that have a fixed delay, but again, we have these internal packet buffers. And then we can set up circuits, or we can set up routes with a given service discipline. Service discipline basically means that how you will ensure a given QoS, in the sense how much of bandwidth will you reserve, and also you can reserve buffers within these uh, routers, right, which is also connected with the broad idea of resource reservation as such. And again, a degree of rate control can be provided, which is basically a model of RT plus B, where the parameter B handles bursts and R is more like a constant rate. So with this, what you can do is that you can, in a sense, provide a degree of bounded access. So we have still not discussed global priority, again because we are dealing with a large distributed system like the internet, but we are essentially ensuring a degree of bounded access in this system. So this will complete the first sub part of this lecture. The second sub part will be in the next video, where we will start from here and then look at the issue of the service discipline.